All right, so we're now going to go on to 8.1.2, formally discussing what the disk method is for finding out the volumes of objects. So the disk method is basically just asking us how we're going to slice up objects. It says here, when slicing a solid such as a lime, the volume can be approximated by slicing an object into shapes that resemble cylinders, calculating the volume of each cylindrical slice, and then adding all the volumes together. However, to get a precise volume, the cylinders must be infinitesimally thin, and it is not practical to calculate the volume of each disk separately. So this is our graph here. It's the square root of x. It says that a typical rectangle is going to be as shown, and we're going to describe the dimensions of this rectangle. So first, we have this is going to be our height, and our dimensions are going to be f of x. That's going to be our height, because if I was to plug in some x value, I'll end up getting a y value, therefore that is going to be the height. And then our width is going to be the amount of x, so the amount of that x changes by. So that's going to be our dimensions of our rectangle. Then we're going to go ahead and reflect our graph, which actually means we're rotating around our x-axis, which then gives us our rectangle that is rotated around, which then will turn this into a cylinder. So our rectangle is turned into three-dimensionally a cylinder. And as you know, a cylinder is going to be, the volume is pi r squared times height. So we are going to use that. It says that when f of x is revolved around the x-axis, the solid in figure B is shown. To calculate the volume of the solid, a typical slice is needed. We're going to write an expression that will calculate the volume of this slice. So since our volume is pi r squared times height, we could then say it's pi. The radius is going to be the height of our triangle, which is f of x. So we'll say this is f of x squared, so r turns into f of x, and then our height is going to be our change in x. So that's going to be our representation in terms of our function. The shape of an infinitesimally thin slice is called a cylindrical disk. Explain how a cylindrical disk is different from a circle. Well, it has some amount of width. It's similar to a cylinder because it is a cylinder, except it's infinitely thin, so it actually doesn't have a width. Since the disk thickness of each disk approaches 0, we can use a definite integral to calculate the volume. So let's go ahead and write the integral that we have here. Our integral from 0 to 8. Now, our area under the curve would normally be represented this integral. And our area would be pi r squared here. But since we have r is going to be our f of x, we're going to say this is pi. And our f of x is the square root of x in this figure. So we're going to say the square root of x squared dx. So we are finding this will give us the volume. The square root of x squared is going to be x. So this is just saying 0, 8, pi. I know it's actually this absolute value of x, but we're going to simplify this as x. So we're going to take the antiderivative of this. Remember that pi is just a number. So what is the antiderivative of x? That's going to be 1/2 x squared. So we could take the pi out. We could say this is from 0 to 8, 1/2 of 8 squared minus 1/2 of, we forgot pi. I want to take pi on the outside. 0 squared. So the second part actually doesn't matter. 8 squared is 64. Cut in half is 32. So 32 pi units cubed. All right, so let's go on to the next one here. We're going to be talking about states of revolution. Let me check the time that I have. Okay. So next, we are going to talk about our next rotation here. If a solid is sliced similar to the previous problem, what is the shape of each slice? So we have a rectangle here, and if we rotate it around, oh look, we get another cylinder. So just as shown here. So this is a cylinder, and the thickness is going to be, so this is a cylinder, and its width is going to be how much x changes, because we don't know how much that is. So this is going to be the change in x is going to be our thickness of our cylinder. Assume that each slice is shown in the diagram is in an arbitrary disk at some x value c between a and b. So c is somewhere here. We don't know where it is between a and b and has some amount of thickness. We want to write an expression for the volume. So the volume of this one is going to be, well, it's a cylinder, so it's pi r squared. R is going to be the height, which is f of x. But instead of x, it's going to be at some value c. So we're going to say this is f of c squared times the change in x. Set up an integral that accumulates the volume of all of these disks. So we're going from a to b. So we'll say a to b. That's going to be our starting and our end point. It is a cylinder, so it's pi r squared. But since it's going to be r, we're going to say f of x squared. So whatever function is making this graph, then we'll say that's f of x. So pi f of x squared, and then dx. And then the last, I think we're going to do two more. So we might have two more. Time for two more. We're going to sketch a region in the first quadrant of g of x equals x squared. So our graph looks like x squared. Bounded by the line x equals 3. Oh, it's in the first quadrant, so I actually don't need this one. Bounded by line equals x equals 3. So 1, 2, 3. This is 3. And then we're going to rotate this around the x-axis. So we're going to rotate it around here. So we end up getting a nice cone guy here. It's going to have some height. The height is going to be 3 squared, which is 9. So it's going to be the radius of our largest endpoint here. The radius of our beginning point is going to be 0. We're going to set up and evaluate the integral. So we are going from 0 to 3. So 0 to 3. Pi r squared. R is going to be our function. Our function is x squared. So we'll say x squared squared dx. This is actually saying x to the 4th, I suppose. So we'll say this is pi x to the 4th dx. The antiderivative of x to the 4th is x to the 5th, and then we'll put a 1/5 in front. Because the derivative of the 5 multiplies by the front, so it cancels out, so we know. We're going to take the pi out. We'll say this is 0 to 3 of 1/5 3 to the 5th minus 1/5 times 0 to the 5th. So 3 to the 5th is what, 120, no, I don't know, 243 or something? 3 to the 5th. It's 243. It's 243. So 243 over 5, because that times divided by 5, pi units cubed. Okay, we're going to do the last one here. I know I'm rushing a little bit fast, but go ahead and pause and watch the video if you need to go over it again. So we've got another function here. This is x squared. So we're going to do the same function up here, but instead, now it's going to be y equals 4. So 1, 2, 3, 4. So this is y equals 4. This time it says it's going to be rotated around the y-axis. So we end up getting some three-dimensional figure that looks like that. So how would we find the radius of this disk instead? So if we say that our f of x equals x squared, when we rotated around the x-axis, we ended up saying that we had cylinders that were in terms of change in x, and that was going to be our thickness. Our thickness was change in x, how much x was changing. So would it make sense then that this is going to be our change in y? Yeah, our thickness for this one's going to be change in y. So how are we going to write the integral for this? Well, we're going from 0 to 4 with a cylinder, but instead this time our function is not going to be, it's not going to be in terms of y. So how do I write that? I have y equals x squared. I have to solve for x because now it's in terms of y. So it's the square root of y equals x. So that's going to be our square root of y squared because it's pi r squared. dy this time, because now we're doing it in terms of y because we're doing height instead and how much y is changing. So this is really saying pi y dy from 0 to 4. The antiderivative of y is going to be y squared with a 1/2 out in front. So we're going to have pi from 0 to 4, 1/2 4 to the squared, minus 1/2 0 squared. And that gives us 16 cut in half is 8, so we get 8 pi units squared. And your assignment for today is just going to be 2 problems. I'll see you later.